So folks, I think that my written explanation for number 5 is sufficient to do what you need to do for this problem. So I'm not going to write out a whole lot for this, but I do want to give just a quick video description. In this case, we've got a rock tied to a string, and it's whirled around, and the rock is going to follow the curve parameterized by this expression right here. And so just to give you a sense of this, I've gone ahead and plotted this in GeoGebra, which is a good way to see some of these 3D curves. You do not need to look at the graph of R of t to be able to answer this question. This is really important because in the problems you'll encounter on exams or in my lab math, you won't be reliant on the image of this curve, but I do want to build our intuition with this. So if you were to click this GeoGebra link, we should get something that pops up like this, and this is meant to model the path of this rock as it's whirled around. And you can twist this around and see what it looks like. The other thing is I can extend the curve so it goes on along further, not there, by clicking this this button here. That would be the continued motion of that rock as it's being whirled around based on based on this function right here. Now, at time t equals pi over 2, the string is cut. So I want you to imagine this rock being whirled around, and then right here when we pass this point, the string breaks or it's cut or whatever. And what's the rock going to do at that instant? Well, the rock is no longer going to be tethered by the string, so it's no longer going to follow the original path that we gave it. And instead, by some of our laws of mechanics, the object in motion remains in motion. This rock is going to start moving in a straight line path. And what do we know about that straight line path? That straight line path will be a path tangent to the curve that described the motion of the rock. And so what I want to point out to you then is that this question is simply asking us to come up with the equation of the line tangent to this curve at time t equals pi over 2. And so I'm going to let you work through this because I think you have all the tools you need. I've simply got a vector valued function, and I'm asking you to compute the equation of the tangent line to this to the line tangent to this vector valued function at time t equals 2 pi. So you can click the solution here and examine that, and please spend your time working through that. But here I can pull it up. And remember that if you want to find an equation to a tangent line, you simply need a point, an initial position vector, and a direction vector. And we're going to get the initial position vector by asking the question, where is the rock at time t equals 2 pi? So we simply compute where is the rock at time t equals 2 pi. We plug 2 pi into the position function for the rock as it moves along the string, and we get this value right here. Then we need to decide in what direction will the rock move, and the rock will move with a direction that is, or will have a direction vector corresponding to the velocity vector of our position curve, or the derivative of our position curve, because the velocity vector is tangent to our position curve. So again, if we go look at the GeoGebra, here is our blue curve in space that's modeling the rock as it's whirled around, and then when we reach time 2 pi, the chord is cut. The rock begins moving in this direction, but the key observation to make is that that direction is tangent to the position curve. And so by computing the tangent vector to this curve, that gives us the direction vector of our tangent line. And so I don't want to do anything more than that. You've got everything you need, but go ahead and work through this example and then let me know what questions you have either in class or in office hours. Thank you, folks.